Okay, so this is what you see as an on-the-ground observer if you are actually in the field at or near the summits of the two Beartown mountains that we just looked at. The one on the left here is the Southwestern Beartown Mountain. It's very impressive because of its red spruce forest near the summit. These are called balsam trees regionally. Very interesting conifers. You only get those at high elevation in the Appalachians. At this latitude, you need about 4,500 feet to start seeing those, and that's approximately the elevation at which this picture was taken. On the right, you're looking at the summit of the Northeast Beartown Mountain, which is actually called sometimes Balsam Beartown Mountain. It's a little bit taller in terms of overall elevation than the Southwestern Beartown, but they're pretty comparable. They're close to each other in the landscape. You find the same sandstone cap rock. It's in a comparable geometry, and that's actually because they are part of the same structural feature within the Appalachian Fold Thrust Belt. And from the vantage point from which this picture was taken, you can actually sort of resolve the role of stratified rock in controlling the geometry of this summit if you know what to look for, of course. This is a very gentle dip slope. This is a steeper scarp slope. But again, as an observer on the ground, you really can't fully appreciate what's going on. You need to look at it with Google Earth, and you need to supplement that with some kind of a structural model to give you a sense of what's going on beneath the surface and how erosional history has produced the patterns that you see here. So there's the Southwest Beartown Mountain. There's Balsam Beartown Mountain. They're pretty close to each other. They're connected by this narrow ridge, but again, you can see that localized plateau geometry that, although it's not particularly steep and jagged and impressive, that's what gives you topographic highs within this landscape. So to get a sense of what's going on, we're going to use this model. It does a pretty good job of giving you a sense of the structural character beneath this part of the Appalachian Fold Thrust Belt. Two pretty high displacement thrust faults, a variable stratigraphy, but very important here is the presence of this really tough and resistant sandstone horizon about halfway up through the section, and beneath that, associated with these purple layers, is really soft and erodible and weatherable carbonate rock. Here in the humid temperate Appalachians, carbonate rock is no good for making high topography. It makes valleys, and this represents a deep carbonate sequence with a much stronger but thinner clastic sequence on top of it. And if you want to take a look at this model and immediately pick up on something that, structurally speaking, will translate to high topography in Appalachia, it's right there. It's that little syncline. It doesn't look like much within the scope of the entire model, but synclines make high elevation, or at least they make high topography relative to adjacent valleys in mechanically variable stratigraphies like this, where you might find a particularly tough rock higher in the section with weaker material below it. So to think of this in terms of erosional history, we'll say that the model as you see it now would represent the deformed Appalachian Fold Thrust Belt at the end of Appalachian deformation. At that time, this is sort of a deformed four-deep or deformed foreland basin. It would have been subsided downward due to the isostatic load from the rest of the mountain range. As erosion of that range reduced some of that loading, also as rifting and opening of the Atlantic Ocean produced considerable crustal disturbance within this area, there would have been considerable erosion. So we could say that that land surface would then carve down deeper into the wedge, and at this point we'll say that that cap rock unit, that tough and resistant sandstone, would be producing some kind of impact on topographic highs, but our syncline feature at this point has not even been exhumed. It has not emerged erosionally yet, and it's not really doing much to topography. But if we run this a step ahead, here we'll say we're looking at a past or previous land surface. This place is always changing, erosion is constant here, and the land surface is progressively moving deeper into this deformed wedge. If we go to the modern land surface, then you see something different. Our little syncline there is now the high point in the landscape, And that's because the land surface has eroded through the caprock material on this big anticline and this big anticline, and the land surface has encountered that very soft and erodible and weatherable carbonate rock and produced very broad and deep valleys where that soft material is exposed. So at this point, it's not unreasonable to visualize this process in terms of thinking that the little syncline here has sort of caught, if you will, caught or trapped or whatever the land surface in the axis of the syncline as it has progressively moved deeper into the wedge where these more erodible rocks are available at the surface. So the syncline here is sort of a trapping point, if you will, for the land surface, again, when more erodible material is available on structural highs adjacent to the syncline. Now, in the future, little syncline finally will become eroded away. The softer rock will be accessed at the surface here, and this syncline will become the topography dominating feature with topographic lows next to it, where that weak and soft and erodible and weatherable carbonate rock is available on the adjacent structural highs. So this is a very basic way of trying to understand what synclines do within a landscape like this that's developed in mechanically variable rock. And that's really the key. If all of this rock was mechanically uniform, you wouldn't quite see patterns developing like this. Certainly the dip of the rock and the orientation of bedding relative to water flowing across it, for example, would impact the way erosion progressed through this wedge. But when you've got really exaggerated contrast like this, particularly with weak material deep in the wedge and resistant material higher in the section, it's pretty well accepted that in a landscape like this, you're going to see the topographic highs within a region stuck, if you will, in synclines like you see here when the erosional surface has carved much deeper into the adjacent more erodible rock that's associated with these big thrust faults here.